The question we have is, could you show us how to calculate strains and displacements for a 1D rod, one-dimensional rod? This is the problem I have chosen here. We have a one-dimensional cylindrical rod subjected to an axial force of 10 kilonewton. The initial length of the rod is 2 meters. The initial diameter of the rod is 20 millimeters. Young's modulus of the material that makes up the rod is 100 gigapascal. Poisson ratio is 0.33. The question has two parts. First, we want to calculate the strains in the x, y, and z direction shown on the picture. Then we want to calculate the final length and the diameter of the rod. First, we will assume that the stress produced by the load is small enough that the rod behaves elastically. Here's my calculation for epsilon x, strain in the x direction. Epsilon x is sigma x over E, but sigma x is P over A, right? Force divided by the cross-sectional area of the rod, and therefore epsilon x is P over AE, right? Now we substitute numbers for these parameters in a consistent way. So P is 10 kilonewton, area of the cross-section is pi times r squared. R would be 10 millimeter. Expressing that in meters, that will be 0.01 meters. So you square that, right? And E is 100 gigapascal. So I'm going to convert that into kilopascal. So to do that, I multiply 100 by 10 to the 6th. So kilopascal is kilonewton per meter square, right? So now you can see all of the units will cancel out to give you no dimension for the strain epsilon x the way it's supposed to be. So you get a value of 3.18 times 10 to the minus 4 for epsilon x. Now using this relationship that involved the Poisson ratio nu, epsilon y is minus nu times epsilon x, right? Poisson ratio is given as 0.33, so we substitute that. And we already have a value for epsilon x. So epsilon y is calculated to be minus 1.05 times 10 to the minus 4. Epsilon x is a tensile strain because the force is a tensile force, and therefore epsilon y is a compressive strain. Epsilon z is given by the same equation, and therefore we have the same value as epsilon y. This is how we calculate the final length. From the definition of normal strain, epsilon x is the displacement delta in the x direction divided by the initial length of the rod in the x direction, right? So in other words, epsilon x is delta over L naught, where delta is L minus L naught divided by L naught. Now if I simplify this a little bit, so L over L naught, right? You kind of separate this into two terms, L over L naught minus L naught over L naught, which is 1, right? Rearranging this equation, we get this expression for L. L equals L naught times 1 plus epsilon x. Now we substitute numbers for the parameters on the right side. So L is calculated to be 2.000636 meters, only slightly different from the original length of 2 meters. Now this is because this is a very stiff bar. The Young's modulus of this material is 100 gigapascal, which is very, very large. Following the same approach, we use the strain either in the y direction or the z direction in order to calculate the final diameter of the rod. We are able to use either the strain in the y direction or the z direction simply because this is a circular cross-section. Therefore, the diameter before and after are the same in both y and z directions. Here I choose to use the strain in the y direction. Epsilon y is delta y over d naught. Delta y is d minus d naught over d naught. So this equation finally simplifies to this expression for the final diameter d. Now you substitute numbers and we get this value for the final diameter, 19.9979 millimeter. Once again, it's only slightly smaller than the initial diameter of 20 millimeters. Now you may want to note that you can either use the diameter in meters or millimeters, it doesn't matter. your final number for the final diameter is going to depend on that. Since I used the diameter in millimeter, my final diameter is also calculated in millimeters.